Good day everyone, I'm John Carlin Balais from College of Engineering and Technology, and the topic that was given to me is halo antenna. And I will be reporting the definition of halo antenna versus other loop antennas, modern versus original halo design, halo versus large loops, halo versus small loops, size, and finally the advantages and disadvantages. So without further ado, let's get started. So when we talk about loop antennas, it's just a simple conductor in loop. And there are two types of loop antennas, which are electrically small loop antennas and large loop antennas. And they may have various shapes like circular or halo, triangular, square, elliptical, and etc. And these antennas are used for both transmission and reception. So what is halo antenna? A halo antenna or halo is a horizontally polarized omnidirectional one-half wavelength dipole antenna which has been bent into a loop with a small break in the loop on the side directly opposite the feed point. The dipole ends are close but do not meet, as you can see on the figure, and may have an air capacitor between them as needed to establish resonance. Typical halo antenna construction. The round tuning plates are tuned for resonance and omitted in some designs. The small box contains a small trimmer capacitor used to fine-tune the gamma match arm. Halo antenna versus other loop antennas. So this section compares older and more recent designs halo antennas. Compares halos to large loops that are twice their size, and compares halos to small loops, which tend to be around half the size of halos built for the same frequency. So question number 1, it is a one-half wavelength dipole antenna which has been bent into a circle with an electrical break directly opposite the feed point. So I'll just leave it to you guys. Next one is modern versus original halo design. Early halo antennas used two or more parallel loops, modeled after a 1943 patent which was a folded dipole bent into a circle. The two-loop design broadens the SWR bandwidth and helps with impedance matching. More recent halo antennas have tended to use a single conductor fed with a gamma match. The newer approach uses less material and reduces wind load, but may be less mechanically robust, more narrow-banded, and requires a balloon to prevent feed line radiation. What type of information can be obtained by submitting the details of a proposed new antenna to a modeling program? Second is which of these matching systems is an effective method of connecting a 50 ohm coaxial cable feed line to a grounded tower so it can be used as a vertical antenna. Next is halo versus large loops. A halo antenna is distinct from a full wave loop, which is double its size or larger, whose element is a complete loop with no breaks. Further, full wave loops radiate predominantly perpendicular to the plane of the loop at their lowest frequency, whereas halos radiate mostly in the loop plane, with some radiation in the perpendicular direction. Unlike full wave loops, halo antennas do not produce much radiation perpendicular to the plane of the loop, but do produce some. Their greatest radiation is in the plane of the loop. Full wave loops produce their highest radiation perpendicular to the loop and almost none in the plane of the loop. Next is halo versus small loops. A halo antenna is distinct from the small loop antenna in size, radiation pattern, and radiation resistance, or efficiency. Halos are customarily operated with the plane of the loop oriented horizontally, parallel to the ground, whereas small loop antennas often are oriented vertically. A small loop antenna designed for transmitting is usually about half the size of a halo built for the same frequency, 1/4 wave in circumference, or a bit smaller. A small loop can be at most a little less than 1/3 wave in circumference, or 2/3 of the size of a halo, and becomes increasingly difficult to tune as it approaches the maximum. Question: what is a folded dipole antenna? So we're still in halo versus small loops. The current profile of a small loop is uniform or very nearly so, whereas the current on the halo antenna is sinusoidal. Almost all the current in a halo antenna is on the side opposite the break in the loop, which is usually also the loop's feed point. The part of the halo near the split has high voltages, but carries essentially no current and produces no radiation. The part opposite the gap is the part that radiates, and tends to radiate slightly more towards the split in the loop, because a wave small loop has essentially the same current flowing in the entire loop. It radiates in the plane of the loop uniformly, with no preferred direction in that plane. Small loops' radiation pattern is the opposite of large loops. They produce their greatest radiation in the plane of the loop, and none in the perpendicular direction, whereas halo antennas do produce some. Halo antennas' radiation pattern, like their size, falls in between large and small loops, although somewhat closer to small loops. Question: which of the following factors determines ground losses for a ground-mounted vertical antenna operating in a 3 to 30 MHz range? What is a disadvantage of decreasing the number of wire segments in an antenna model below the guideline of 10 segments per half wavelength? Size is relative. Since antenna size is measured in multiples of wavelengths, a halo antenna with sufficient capacitance to operate a half its design frequency will function as a small loop. Likewise, a small loop fed with a signal at approximately double its maximum design frequency will function as a halo antenna. If its reactance can be tuned low, design frequency will function enough. If its reactance can be tuned low enough to resonate, or the excess reactance removed by a matching unit. In that sense, even though built to deal with different practical constraints, the two types of loop antenna are nearly identical. The only two issues are: number one, how well the loop plus impedance matching system plus radio can accommodate the reactance of a frequency the antenna was not designed for. Number two is whether the capacitance across the halo's gap is enough to allow a near continuous current around the loop at below design frequencies. Next is advantages and disadvantages. Like all antennas designs, the halo antenna is a compromise that sacrifices one desirable quality for another even more desirable quality. For example, halos are small and efficient, but only for a single frequency and a small band around it. The following sections discuss the advantages and disadvantages of halo antennas, both for practical and theoretical issues. So, the advantages of halo antenna. When constructed correctly, the antenna will present a good match to a 50 ohm coaxial cable with a low SWR. Towards the horizon, the pattern is omnidirectional to within 3 decibel or less, and that can be evened out by making the loop smaller and adding more capacitance between the element tips. Not only will that even out the gain, it will reduce the largely wasted upward radiation. The next is radiating element of the halo is grounded, which tends to reduce static buildup and advantage shared by many antennas fed with a gamma bunch. Next is on the VHF bands and above, the physical diameter of a halo is small enough to be effectively used as a mobile antenna. Next, halos may be stacked for additional gain. And this reduces the high angle radiation but has little or no effect on the shape of radiation pattern in the plane of the antenna. Next is halos pick up less ignition noise from vehicles when mounted atop vehicle roofs than whip antennas. And the last is halo antennas have lower voltages across their caps than small loop antennas fed with the same power, reducing problems with um, arcing and electric shock, and radiate more efficiently than small loops. Disadvantages: radiation from horizontal halos has small no vertical component. One can expect 3 to 20 decibel of signal loss when working loose when working with the stational using vertical polarization. For mobile use, the halo is rather conspicuous compared um, to the much more common vertical whip antenna and may attract unwanted attention. The halo is a grid structure and may suffer damage from tree branches or other obstacles in mobile operation. A halo antenna can function as designed as a resonant half-wave antenna only at one frequency, limiting its use to a single band or only a part of one band. A small transmitting loop can be retuned to a range of frequencies typically wider than 2 to 1 approaching 3 to 1, which can cover 2 or 3 different amateur bands. Lastly, is a halo antenna is not uh, as efficient for distance contact via skywave as a horizontal small loop. Other things being equal, since more of its signal is sent upward instead of upward, raising signal power, warming the clouds. Question: which of the following is not an advantage of halo antenna? So the summary is, although it has a superficially similar appearance, the so-called halo antenna is not technically a loop since it possesses a break in the conductor opposite the feed point. The totally changes the current pattern since the voltages across the break are opposite and large. It is better analyzed as a dipole, which also has a large voltage and zero current at its end, which has been bent into a circle and end loaded with a low capacitance air capacitor. So that's the end of presentation. Thank you for listening.